Hello everyone, I'm Zihan from ICT Cares. Today my topic is how to use HPC AI500. I'll first introduce the general steps to use HPC AI500. The current release of HPC AI500 is version 2, which is publicly available from Bench Council HPCI websites. The reference implementation is on the Bench Hub, the official code repository. The general steps to run the benchmark are as following. First, download the reference implementation on BenchHub. Second, prepare the dataset environment according README. We have packaged all the dependencies into a Docker, which is more convenient for everyone to configure the environment. Third, running the scripts, including training, evaluation, and inference. Current HPC 500 consists of component benchmarks and micro benchmarks. Today, I'll focus on the component benchmarks. The component benchmarks include extreme weather analysis and image classification. Next, we start with the component benchmarks, taking extreme weather analysis as the example. First of all, I will introduce some background knowledge of this workload. Extreme weather analysis poses a great challenge to human society. It brings severe damage to people's health and the economy every single year. For instance, the heat waves in 2018 caused over 1,600 deaths according to the UN report, and the landfall of Hurricane Florence and Michael cost about $40 billion worth of damage to U.S. economy. In this context, understanding extreme weather life cycle and even predicting its future trend become a significant scientific goal. Achieving this goal always requires accurately identifying the weather pattern to acquire the insight of climate change based on massive climate data analysis. The following are 4 common extreme weather events, such as tropical depression and atmospheric river, etc. Traditional climate data analysis methods are built upon human expertise in defining multivariate thresholds of extreme weather events. However, it has a major drawback. There is no commonly held set of criteria that can define a weather event due to the man-made subjectivism, which leads to inaccurate pattern extraction. Therefore, deep learning has become another option for climate scientists. As shown in the figure, the original weather images has been processed to the labeled one, which is essentially an object detection task. The EWA dataset is made up of 26-year climate data. The data of every year is available as one HDF5 file. You can obtain this data by Globus endpoint. Each HD5 file contains 2 datasets, images and boxes. The image dataset has 460 example images with 16 channels. These channels are quite different from commercial datasets such as ImageNet, as it includes many physical information instead of visual information, such as surface pressure and temperature, as shown in the right figure. Each channel is 768 and 1152 resolution, corresponding to one measurement per 25 square kilometers on Earth. The more details can be found in this website. In this extreme weather dataset website on GitHub. The adopted model is FastRCN and is FPN version, using ResNet 50 to extract features. FastRCN targets real-time object detection. As one of the latest models of an RCN family, it deprecates the selective search used in the previous RCN version. Instead, FastRCN proposes a dedicated convolution neural network named Region Proposal Network, RPN for short, to achieve nearly cost-free region proposals. With such a design, object detection is much faster. As a result, FastRCN wins the first place in ILSVRC 50. The specific layer information can be found in the model description file. Next, I'll introduce the running steps. The first running step is data pre-processing. The implementation needs the data to be processed to COCO format. Therefore, we provide two scripts to this work. The first one is HDF to JSON.Python. Is a file that is responsible for generating JSON file of COCO format. The second one is responsible for generating 16-channel TIFF images. More information about COCO format can refer to its official website. The second step is the environment installation. We provide a Docker file that contains all the dependencies. Users can build a Docker image based on this Docker file and then start running this by this command. We also provide the training script to perform distributed training. Our implementation is based on OpenMPI and Oracle. After training, we can execute predict script to check the model quality. The result is shown in the screenshot. As for the metrics, we can get the time to accuracy by the script. Time to accuracy shell script. As shown in the figure, the time to accuracy is about 6,000 seconds. Next, we introduce how to calculate valid flops. We get training time and accuracy through the reported time to accuracy. Then we can calculate the flops by training time as the following formula. In extreme weather analysis, the batch size is 1 and the flops per image is 691 G flops. Finally, we can get the valid flops by the following formula. In extreme weather analysis, the n is set to 10 and the target quality is set to MAP equals to 0.35. In addition to the time to accuracy and the valid flops, we also can obtain other metrics from TensorGraph, such as training loss and the achieved quality. Finally, I introduce the visualization. We provide a visual interface to display the training results. It can be started by the Python script displayed by the slide. As you can see, in this figure, TD, TC, EC, and AR represent the 4 extreme weather patterns just mentioned. My presentation ends here. Thank you for listening.